On Christmas Eve 2024, while most of the world was preparing for holiday celebrations, a small spacecraft was hurtling toward an appointment with destiny of 430,000 miles per hour. NASA's Parker Solar Probe was about to become the fastest object ever built by human hands. Its destination, the outer atmosphere of the Sun itself, just 3.8 million miles from the surface of a star that burns at 27 million degrees Fahrenheit. And it survived. 3 days later, when the probe's beacon signal finally reached Earth, it carried with it something remarkable. Not just confirmation that this washing machine-sized spacecraft had threaded the needle through temperatures exceeding 2,500 degrees, but data from a place no human instrument had ever visited before. We had touched a star, and what we found there is changing everything we thought we knew about the nuclear furnace at the center of our solar system. The images from that closest approach, released in the months that followed, showed details never before visible. Streams of plasma flowing outward, magnetic field lines twisting and reconnecting, material falling back toward the Sun after eruptions. For the first time, humanity was seeing our star from inside its own atmosphere. And what we learned is this: the Sun is even more dynamic, even more complex, even more beautiful than we had imagined. Because here is the thing about the Sun that nobody tells you. It is not behaving the way scientists predicted. Solar cycle 25, the current 11-year pulse of our star's magnetic heartbeat, was supposed to be quiet, weak, unremarkable. In December 2019, an international panel of experts convened by NASA and NOAA looked at the evidence and made their prediction. After decades of declining activity, solar cycle 24 had been the weakest in over a century. They expected more of the same. Modest sunspot numbers, unremarkable flare activity, a gentle maximum somewhere around 2025, then a quiet decline toward the next minimum. Instead, the Sun has been throwing a tantrum. Over 50 X-class flares in 2024 alone. The most powerful geomagnetic storm in over 2 decades. Auroras visible from Florida, from Mexico, from places where the northern lights have no business appearing. And as we enter 2026, the activity is not slowing down. If anything, it is intensifying. So the question becomes urgent. Is this normal? Is the Sun doing something unprecedented? And if it is, should we be worried? The answer, as it turns out, depends entirely on what you mean by worried. If you mean, should we expect the world to end? No. The Sun has been producing solar storms for billions of years, and Earth has weathered them all. Our planet's magnetic field provides substantial protection. The atmosphere absorbs most of the dangerous radiation. Life has persisted through far worse than anything solar cycle 25 has produced. But if you mean, should we pay attention, prepare, and take the risks seriously? Then yes, absolutely. To understand what the Sun is doing right now, you first need to understand what the Sun actually is. Not poetically, not a ball of fire, or the source of all life. Physically, the Sun is a thermonuclear reactor. At its core, hydrogen atoms are being crushed together with such tremendous force, the gravitational pressure of 333,000 Earths worth of mass, that they fuse into helium. Every second, the Sun converts roughly 600 million tons of hydrogen into 596 million tons of helium, the missing 4 million tons. That becomes energy, pure energy, released according to Einstein's most famous equation, E equals mc squared. This process generates about 384.6 septillion watts of power. That is a 384 followed by 24 zeros. The human mind was not designed to comprehend numbers like this. So let us try a comparison. All the electricity humanity generates, every power plant, every dam, every solar panel, every windmill, everything, amounts to about 28 terawatts. The sun produces more energy in 1 second than human civilization has generated in its entire history. And it has been doing this continuously for 4.6 billion years. But here is what most people do not realize. The sun is not a simple sphere of burning gas. It is a complex, layered, magnetically turbulent object that is constantly generating, twisting, and releasing colossal magnetic fields. And it is these magnetic fields, not the nuclear fusion itself, that drive the behavior we are now witnessing. Think of it this way. If nuclear fusion is the sun's heartbeat, its magnetic field is its nervous system. And right now, that nervous system is going haywire. The discovery of the sun's magnetic cycle happened almost by accident. In 1843, a German amateur astronomer named Samuel Heinrich Schwabe was engaged in a seemingly pointless obsession. For 17 years, he had been meticulously counting sunspots, the dark blemishes that occasionally appear on the sun's surface. Nobody thought this mattered. Sunspots had been observed since ancient times, dismissed as imperfections, curiosities, footnotes in the astronomical record. But Schwabe noticed something strange. The number of sunspots was not random. It rose and fell in a predictable rhythm. About 11 years from peak to peak, from quiet sun to active sun and back again. He had discovered the solar cycle. What Schwabe could not know, what no one would understand for another century, was why this happened. The explanation required tools and concepts that did not exist in 1843. Magnetohydrodynamics, plasma physics, the realization that the sun is not solid, but rather a churning sea of electrically charged gas. Here is the modern understanding. The sun is made of plasma, matter so hot that electrons are stripped from atoms, leaving behind a soup of charged particles. This plasma does something peculiar. It drags magnetic field lines with it as it moves. And because the sun is not solid, different parts of it rotate at different speeds. The equator completes one rotation every 25 days. The poles take 35 days. This is called differential rotation, and it has a profound consequence. Imagine taking a rubber band, attaching one end to the equator and one to the pole, and then spinning the equator faster. The rubber band stretches, it twists, it gets wound tighter and tighter around the sphere. This is essentially what happens to the sun's magnetic field. The field starts out relatively simple, like a bar magnet with field lines running from pole to pole. Solar physicists call this the poloidal configuration. But the differential rotation stretches these field lines, wrapping them around the sun like thread around a spool. Over many rotations, the north-south field lines become increasingly wound up in the east-west direction, what scientists call toroidal configuration. This transformation from poloidal to toroidal is called the omega process, and it is one of the two fundamental mechanisms driving the solar dynamo. But the story does not end there, because a toroidal field alone is not stable. It keeps winding up, getting tighter and tighter until something has to give. Deep within the sun, at the base of the convection zone, roughly 200,000 kilometers below the surface, there exists a thin layer called the tachocline. This is where the turbulent, churning convection zone meets the stable radiative interior. The physics here are extraordinary. Intense magnetic fields generated by the winding process become concentrated into structures called magnetic flux tubes. Imagine them as invisible ropes of magnetism, each containing field strengths thousands of times stronger than Earth's magnetic field. These flux tubes are buoyant. They want to rise. Think about what happens when you submerge a beach ball underwater. The moment you release it, it rockets to the surface. Magnetic flux tubes behave similarly. The magnetic pressure inside them reduces the gas pressure, making the plasma inside less dense than its surroundings. They begin to float upward through the convection zone, but the journey takes time. The flux tubes must navigate through 200,000 kilometers of roiling plasma. As they rise, they are buffeted by convective motions. They twist, they fragment into smaller strands. The Coriolis force, generated by the sun's rotation, imparts a characteristic tilt to these rising magnetic structures. Eventually, after weeks or months, the strongest flux tubes break through the photosphere, the visible surface of the sun. When they do, they create sunspots. But here is the crucial detail. Flux tubes pierce the surface in pairs. One end emerges from the photosphere, loops up through the solar atmosphere, and plunges back down at another location. These two penetration points become a pair of sunspots with opposite magnetic polarity, one positive, one negative, leading and following spots in a bipolar pair. This is not random. In the sun's northern hemisphere, during any given 11-year cycle, all the leading spots have the same polarity. All the following spots have the opposite polarity. In the southern hemisphere, the pattern is reversed. And then, at solar maximum, something remarkable happens. The polar magnetic fields, which had been relatively stable, begin to weaken. New magnetic flux, carried poleward by surface flows called meridional circulation, cancels out the old polar field. The poles eventually reverse. What was north becomes south. What was south becomes north. The sun has flipped. This is why solar physicists speak of a 22-year magnetic cycle rather than an 11-year sunspot cycle. It takes two successive cycles with opposite magnetic polarities to return the sun's global field to its original configuration. When Todd Hoeksema, director of Stanford's Wilcox Solar Observatory, monitors the sun's polar magnetic fields, he is watching this process unfold in real time. The poles are a herald of change, he has noted. Just as Earth scientists watch polar ice for signs of climate change, solar physicists watch the sun's magnetic poles for signs of how the cycle will develop. Sunspots are not holes in the sun. They are regions where intense magnetic fields are literally suppressing the normal convection of heat from below. Less heat reaches the surface in these areas, so they appear darker, though darker is relative. A sunspot is still about 6,300 degrees Fahrenheit. If you could somehow cut one out of the sun and place it alone in the night sky, it would shine brighter than the full moon. But sunspots are just a visible symptom of a deeper magnetic turbulence. And when that turbulence becomes severe enough, something far more dramatic happens. The magnetic field lines, stretched to their breaking point, suddenly snap and reconnect. In a fraction of a second, the stored magnetic energy is released in an explosion of light and radiation. This is a solar flare. And when the reconnection is violent enough, it does not just release energy, it throws billions of tons of solar material into space. This is a coronal mass ejection. And when that material is aimed at Earth, that is when things get interesting. On the morning of September 1st, 1859, A 33-year-old English astronomer named Richard Carrington was doing what he did every clear day, projecting an image of the sun through his telescope onto a screen, carefully sketching the positions of sunspots. At 11:18 a.m., something happened that no one had ever witnessed before. Two brilliant patches of white light erupted from within a large sunspot group. They intensified rapidly, became blindingly bright for about 5 minutes, then faded. Carrington knew instantly that he had seen something unprecedented. He later wrote that it was like watching a single swallow. You could not be sure if it heralded summer. He was not alone. Across London, amateur astronomer Richard Hodgson, working independently with his own telescope, observed the same phenomenon. The fact that two observers recorded the events simultaneously was crucial. It proved the flare was real, not an artifact of one observer's equipment. Carrington rushed to present his findings. At the November 1859 meeting of the Royal Astronomical Society, he and Hodgson displayed their drawings side by side, showing the same features in the same positions on the sun. It was the first documented observation of what we now call a solar flare. But Carrington made an even more significant observation. He noted that the Kew Observatory magnetometer had registered a sudden disturbance at almost exactly the moment he witnessed the flare, what scientists now call a magnetic crochet or solar flare effect. This was direct evidence that something happening on the sun could affect instruments on Earth, 93 million miles away. 17 hours later, summer arrived. The magnetic storm that struck Earth on September 2nd, 1859, remains the most powerful geomagnetic event ever recorded. Auroras appeared in the tropics. People in Cuba, in Hawaii, in Colombia, reported the sky on fire with otherworldly light. In the Rocky Mountains, gold miners woke at 1 a.m., convinced by the brilliant glow that morning had arrived, and started making breakfast. The reports from that night are extraordinary even by modern standards. In New York City, observers reported that the aurora illuminated the streets so brightly the newspapers could be read by its light. The New York Times described the sky as constantly changing, with brilliant hues, and the whole heavens illuminated with a brilliant light. Crowds gathered in the streets to watch the spectacle. Similar reports came from around the world. In London, the aurora was visible despite the city's notorious smog. In Santiago, Chile, normally far too close to the equator for auroral displays, residents watched in amazement as the southern lights painted the sky. But it was what happened to technology that shocked the world. In 1859, the cutting edge of human technological achievement was the telegraph. Lines had been strung across continents. Messages could be sent in minutes that previously took weeks. It was, in every meaningful sense, the first iteration of our connected world. And on September 2nd, it all went haywire. Telegraph operators reported sparks flying from their equipment. Some received electrical shocks. Several telegraph stations caught fire. Messages became garbled or impossible to send. But here was the strangest part. At the Boston Telegraph Office, operators tried something remarkable. They disconnected their batteries, the power source for the entire system, and discovered that they could still send messages. The electromagnetic energy being generated by the storm was actually powering the lines. A conversation between Boston and Portland, Maine was documented. Please cut off your battery entirely for 15 minutes. We'll do so. It is now disconnected. Mine is disconnected, and we are working with the auroral current. How do you receive my writing? better than with our batteries on. They were running the telegraph on starlight, or rather, on the electric currents induced in the wires by a magnetic storm emanating from 93 million miles away. We now call this the Carrington Event, and understanding it is crucial to understanding why scientists are paying such close attention to what the Sun is doing right now. But the Carrington Event was not an isolated incident. It was one data point in a long history of the Sun's violence. In 774 AD, something happened that left its signature in tree rings around the world. Japanese physicist Fusa Miyake, analyzing ancient cedar samples, discovered a sudden 12% spike in carbon-14 concentrations, the fingerprint of an intense shower of cosmic radiation. Further investigation revealed similar signals in European and North American trees, and in beryllium isotopes trapped in Antarctic ice. The Miyake event, as it is now called, was approximately 20 times more intense than typical solar activity. Had it occurred in the modern era, the consequences would have been catastrophic, though there were no telegraph lines in 774 AD, so whatever aurora displays might have occurred went largely unrecorded. Similarly, the Great Storm of February 1872 created auroras visible at low latitudes for multiple nights and caused widespread telegraph disruptions. The storm of May 1921, sometimes called the Great Railroad Storm because it disrupted rail signaling systems, was comparable to the Carrington Event by some measures. In August 1972, a series of powerful solar flares and CMEs disrupted communications during the Apollo era. Had astronauts been in transit between Earth and Moon, the radiation exposure could have been dangerous. These events are not anomalies. They are the normal behavior of a variable star. What makes the Carrington Event particularly significant is not that it was unique, but that it was uniquely documented. Carrington's observation of the white light flare, combined with Balfour Stewart's magnetometer readings at Kew Observatory and Elias Loomis's compilation of aurora reports, created a comprehensive record that scientists can still analyze today. And that record tells a sobering story. The Carrington Event was not just historically significant, it was a warning. Here is the physics. When a coronal mass ejection strikes Earth's magnetosphere, the bubble of magnetic field generated by our planet's molten iron core, it compresses and distorts that field. This compression generates electric currents in any conductive material. In 1859, that meant telegraph wires. Today, it means everything. Power lines, transformers, oil and gas pipelines, communication cables, the electrical systems of satellites, the entire technological infrastructure of modern civilization. The scale of the problem has changed by orders of magnitude. In 1859, the world had about 100,000 miles of telegraph wire. Today, North America alone has over 200,000 miles of high-voltage transmission lines. The global electrical grid has grown by a factor of several thousand. And here is the critical vulnerability: extra high-voltage transformers. These massive pieces of equipment are the linchpins of modern electrical distribution. They step voltage up or down, enabling electricity to be transmitted efficiently over long distances. An EHV transformer can weigh several hundred tons and cost millions of dollars. They are manufactured in only a handful of facilities worldwide. Lead time for ordering a new one can be a year or more, and they are exquisitely vulnerable to geomagnetically induced currents. When a solar storm compresses Earth's magnetic field, It generates currents that flow through the ground and into anything conductive. The physics is straightforward. A changing magnetic field induces an electric field, according to Faraday's law of electromagnetic induction. That electric field drives currents through conductive materials, rock, soil, and anything metallic. These geomagnetically induced currents, or GICs, can exceed 100 amperes, the equivalent of the electrical service provided to many households, and they find their way into power systems through the neutral grounding points of transformers. Here is why that matters. Power transformers operate using alternating current. The voltage oscillates back and forth at 60 cycles per second in North America, 50 cycles in most of the world. The transformer's core is designed to handle this oscillating current efficiently, magnetizing and demagnetizing in rhythm with the AC waveform. But GICs are essentially direct current. They flow in one direction for extended periods. When DC enters a transformer designed for AC, it shifts the operating point of the magnetic core. The core begins to saturate on one half of each AC cycle. This asymmetric saturation generates intense magnetic flux that spills outside the normal core path. The results can be devastating. Hotspots develop in structural components that were never designed to carry magnetic flux. Oil inside the transformer heats rapidly. Windings can melt. Gases build up that can be detected by monitoring equipment if the utility is watching. And in extreme cases, the damage is catastrophic and permanent. A single extra high voltage transformer can take 18 months to manufacture and cost $10 million or more. There are only a few facilities worldwide capable of producing them. They must be transported by specialized equipment because of their enormous size and weight. The logistics of replacing even a few dozen simultaneously damaged transformers would be unprecedented, and a Carrington-level storm would not damage a few dozen transformers. It could damage hundreds, perhaps thousands. This is not theoretical. On March 13, 1989, a geomagnetic storm caused the complete collapse of the Hydro-Quebec power grid in Canada. 6 million people lost electricity for 9 hours. The cascading failure took just 90 seconds to take down 21 gigawatts of generating capacity. Transformers were damaged. A replacement unit in New Jersey, which was particularly hard hit, cost over $10 million. The story of those 90 seconds is instructive. At 2:44 a.m. Eastern Time, the geomagnetic storm struck. Earth's magnetic field compressed violently, and geomagnetically induced currents began flowing through the ground and into power infrastructure across northeastern North America. In Quebec, the situation was particularly acute. The province sits atop the Canadian Shield, a vast formation of ancient igneous rock that does a poor job conducting electricity. When GICs flowed through the ground, they found an easier path: the high-voltage transmission lines of Hydro-Quebec. These lines carried power from the massive James Bay hydroelectric project in the north to population centers in the south. They were long, exactly the characteristic that makes transmission lines vulnerable to geomagnetically induced currents, which are proportional to the length of the conductor. At 2:44:17 a.m., the first problem appeared: unusual voltages on the Lagrange transmission network. Within seconds, static VAR compensators, devices that regulate voltage stability, began tripping offline. One after another, 7 compensators shut down as the GIC-induced harmonics overwhelmed their protective systems. With the compensators gone, voltage on the network became unstable. It dropped dramatically. Within less than a minute, all 5 transmission lines connecting the James Bay generators to Montreal tripped due to loss of synchronization. The entire northern generating complex disconnected from the grid. Now, the southern portion of the grid was drawing power that the north could no longer supply. Frequency began to drop. Generators that sensed the frequency instability began disconnecting automatically to protect themselves. A cascade of protective trips spread across the network. By 2:45:52 a.m., just 92 seconds after the first problem appeared, the entire Hydro-Quebec system was dark. 6 million people woke to find no electricity. In the depths of a Canadian winter, with outside temperatures well below freezing, heating systems failed. Traffic lights went dark. Subway systems stopped. Hospitals switched to emergency generators. The blackout lasted until approximately noon, 9 hours later. But the full restoration of the grid took days, and the damage extended beyond Quebec. Across the border in the United States, over 200 anomalies were reported on power systems during the first few minutes of the storm. A $10 million transformer at the Salem nuclear plant in New Jersey was damaged beyond repair, and the March 1989 storm was perhaps 1/3 as intense as the Carrington Event. A 2013 report commissioned by Lloyd's of London estimated that a Carrington-level storm today could cause between 0.6 and 2.6 trillion in damage to the United States alone. Between 20 and 40 million Americans could be without power for periods ranging from 16 days to 1 to 2 years. Because if enough transformers fail simultaneously, there simply are not enough spares. The manufacturing capacity does not exist to replace them quickly, and without electricity, the cascade of failures accelerates. Water treatment plants stop working. Refrigeration fails. Fuel pumps at gas stations cannot operate. Communications break down. The National Academy of Sciences has described the scenario in stark terms. Extensive social and economic disruptions, with recovery times measured not in weeks, but in years. So when scientists say the sun is behaving strangely, when they note that solar cycle 25 has dramatically exceeded predictions, this is what they are thinking about. Let us be precise about what is happening. In December 2019, an international panel convened by NASA and NOAA made their official prediction for solar cycle 25. Based on decades of observation and the best available models, they forecast that this cycle would be similar to its predecessor, solar cycle 24, which had been the weakest in over a century. The predicted peak was modest, about 115 sunspots at solar maximum, occurring around July 2025. This prediction has proven spectacularly wrong. The reasons for this failure are instructive. Solar cycle prediction is one of the most challenging problems in space physics. Scientists use a variety of methods, from empirical correlations with past cycles to sophisticated computer simulations of the solar dynamo. But the sun is a complex system, and our observations of its interior are indirect at best. The most successful predictor historically has been the strength of the sun's polar magnetic field at solar minimum. A stronger polar field tends to produce a stronger subsequent cycle. But even this relationship has significant uncertainty. Some researchers, using alternative methods, did predict a stronger cycle. Scott McIntosh and Robert Lehman, working at the National Center for Atmospheric Research, used a technique based on timing of magnetic terminators. moments when the old cycle's magnetic activity dies out completely. Based on the December 2021 Terminator, they predicted a peak sunspot number of 185, nearly 60% higher than the panel prediction. "I'm not going to gloat," Lehman said, as the cycle exceeded expectations, "but the sun is certainly a lot more active than the panel consensus." The discrepancy between predictions highlights just how much we still have to learn about our nearest star. After 4 centuries of telescopic observation and decades of space-based monitoring, fundamental aspects of the solar cycle remain mysterious. By January 2023, sunspot activity was already running 12% higher than Cycle 24 at the same point. By the end of 2025, Cycle 25 was averaging 31% more sunspots per day than its predecessor. The peak, when it came in October 2024, substantially exceeded the panel's forecast. But it was not just the sunspot numbers that surprised scientists. It was the violence. May 2024 brought the most intense geomagnetic storm since the Halloween storms of 2003. A large and complex sunspot group designated AR36664, spanning an area more than 16 times wider than Earth, unleashed a barrage of X-class flares over several days. At least 7 coronal mass ejections were directed at our planet. The result was a G5 geomagnetic storm, the first rated extreme in over 2 decades. The mechanics of what happened are instructive. Active region AR36664 was not just large, it was magnetically complex. Solar physicists use classification systems to describe sunspot groups, and AR36664 qualified as one of the most complex configurations, a beta-gamma-delta region, meaning it contained multiple spots of opposite polarity in close proximity with tangled, highly stressed magnetic field lines. This is precisely the configuration that produces the most powerful flares. When magnetic field lines reconnect in such a region, the energy release is staggering. The X-class flares produced by AR36664 released energy equivalent to billions of 1 megaton nuclear bombs, though this comparison, while technically accurate, fails to convey the true scale. A better comparison might be this. In a few minutes, a major solar flare can release as much energy as humanity has generated in all of recorded history. But the flares themselves, while dramatic, were not the primary cause of the geomagnetic storm. Solar flares release electromagnetic radiation that travels at the speed of light, reaching Earth in about 8 minutes. This radiation ionizes the upper atmosphere and can cause radio blackouts, but it does not generate geomagnetic storms. The storms come from the coronal mass ejections. When AR36664 erupted, it threw billions of tons of magnetized plasma into space. Multiple CMEs were launched over several days. Some traveled faster than others, and as the faster CMEs caught up with the slower ones, they merged, a phenomenon scientists call CME cannibalism. This interaction is crucial. When CMEs merge, they can concentrate their magnetic energy and arrive at Earth as a single, more powerful disturbance. Historical research has shown that the most extreme geomagnetic storms, including the Carrington Event itself, often involve multiple successive CMEs that interact during their transit through interplanetary space. The merged CME from May 2024 hit Earth's magnetosphere with an interplanetary magnetic field strength of 73 nanotesla, with a sustained southward component reaching 50 nanotesla. The significance of that southward orientation cannot be overstated. Earth's magnetic field points roughly northward. When an incoming CME carries a magnetic field that also points northward, the fields tend to repel each other, and the storm effects are minimal. But when the CME's field points southward, opposite to Earth's. The fields can connect through a process called magnetic reconnection. Energy pours into the magnetosphere. Charged particles flood into the polar regions. The aurora intensifies, and geomagnetically induced currents surge through ground-based infrastructure. The auroras that night were visible from Florida, from Mexico, from Puerto Rico, from places where residents had never seen the northern lights and might never see them again in their lifetimes. Social media filled with images. Amateur photographers captured colors their eyes could barely perceive. Deep reds and purples and greens undulating across skies that normally showed only stars. It was beautiful. It was also a reminder. The storm caused measurable impacts. GPS systems degraded. High-frequency radio communications blacked out. Satellites experienced anomalies. One agricultural equipment company, John Deere, reported that precision GPS systems used for planting were disrupted, a problem that cost affected farmers an average of $17,000 each during the critical spring planting season. Research later revealed that the storm caused unprecedented changes in Earth's ionosphere. Electron density over China dropped by up to 98% in some regions and took over 2 days to recover. The implications for radio propagation and navigation accuracy are still being studied. This ionospheric depletion was remarkable. The ionosphere, the electrically charged layer of atmosphere extending from about 60 kilometers to over 1,000 kilometers altitude, is essential for long-distance radio communication. Radio waves bounce off the ionosphere, allowing signals to travel around the curve of the Earth. When the ionosphere is disrupted, this propagation fails. The May 2024 storm demonstrated just how severely the ionosphere can be affected. Chinese scientists, using data from the Chinese Meridian Project, a network of ground-based and space-based instruments monitoring Earth's space environment, documented the most extreme ionospheric depletion ever recorded. The depletion showed pronounced asymmetry between hemispheres, with the northern hemisphere more severely affected. Recovery took well over 48 hours. During this period, high-frequency radio communication was severely impaired over vast regions. These findings have implications beyond amateur radio enthusiasts. Emergency services, maritime communication, aviation over oceans, and military communications all rely on HF radio in certain circumstances. Understanding how solar storms affect the ionosphere is critical for maintaining these essential services during extreme space weather events. And then, November 2025 brought another wave, an X5.1 class flare, the strongest of the year, triggered a G4 storm with auroras visible as far south as Arizona, Texas, and Florida. Just 3 days later, another X4 class flare followed from the same sunspot region. The sun, it seemed, was not finished. So what is happening? Is this unprecedented? Should we be alarmed? Let us address these questions in order. First, what is happening? The sun's behavior, while exceeding predictions, is not fundamentally outside the range of historical variability. Solar cycles are notoriously difficult to forecast. The prediction panel that convened in 2019 synthesized nearly 50 different prediction methods, and they varied wildly. Some suggested cycle 25 could be very weak, others that it might be quite strong. The problem is that we still do not fully understand the solar dynamo, the mechanism by which the sun generates its magnetic field. We know the basic physics: differential rotation, convection, the interplay between poloidal and toroidal magnetic field configurations, but the details remain frustratingly elusive. Lisa Upton, co-chair of the Solar Cycle Prediction Panel and a solar physicist at the Southwest Research Institute, has noted that Cycle 25 activity has slightly exceeded expectations, but emphasizes that this does not indicate anything fundamentally abnormal. The sun is variable. Sometimes cycles run hot. Second, is this unprecedented? No. While Solar Cycle 25 has been more active than its immediate predecessor, it remains well below historical averages. The modern maximum, a period of unusually strong solar activity spanning roughly 1900 to 2000, saw cycles that were considerably more intense. Solar Cycle 19, which peaked in 1958, had a smooth sunspot number of over 200. We are nowhere near that level. The Carrington Event occurred during Solar Cycle 10, which peaked with a sunspot number of only about 98, lower than current activity. Extreme solar storms can happen during any cycle. What matters is not the average activity level, but whether a particular active region happens to produce a particularly violent eruption aimed at Earth. This brings us to the third question. Should we be alarmed? Here, the answer becomes more nuanced. The honest answer is that we should not be panicked, but we should absolutely be prepared. The sun is doing what the sun does. It has been producing solar flares and coronal mass ejections for billions of years. Earth's magnetic field provides substantial protection. The atmosphere shields us from radiation. Life on this planet has survived far worse than anything we are currently experiencing. But our technology has not. The vulnerability is real. It is measurable, and it is growing. Every year, we become more dependent on systems that are susceptible to geomagnetic disturbance. The global fleet of satellites now numbers in the thousands, with Starlink alone operating over 6,000 spacecraft. The electrical grid continues to expand and interconnect. GPS has become woven into the fabric of modern life, not just for navigation, but for precise timing signals that underpin everything from financial transactions to cellular networks to power grid synchronization. Consider for a moment all the ways GPS affects modern life. When you use a credit card, the transaction is time-stamped using GPS-derived timing. Stock exchanges synchronize their clocks using GPS. Cellular networks coordinate handoffs between towers using GPS. Power grid operators use GPS to synchronize voltage phase across vast distances, a critical function that, if disrupted, could cause cascading failures. This dependency has grown so pervasive that most people are completely unaware of it. The May 2024 storm provided a glimpse of what happens when GPS becomes unreliable. Precision agriculture systems failed. Drone operators reported losing control of their aircraft. Survey equipment malfunctioned. Container ports and shipping logistics were affected. And GPS degradation was just one effect among many. When charged particles from the sun stream into Earth's atmosphere, they ionize the upper atmosphere, the ionosphere. This changes how radio waves propagate. High-frequency radio, used by aircraft over oceans and by emergency services in remote areas, can be completely blacked out. Amateur radio operators reported widespread disruption during the May 2024 event. Satellites face multiple threats. Solar flares release intense bursts of X-ray and ultraviolet radiation that ionize Earth's upper atmosphere, causing it to expand. This increases atmospheric drag on satellites in low Earth orbit. During geomagnetic storms, satellites must use more fuel to maintain their orbits. In February 2022, a minor geomagnetic storm caused 38 of 49 newly launched Starlink satellites to fall out of orbit before they could reach their operational altitude, a loss worth millions of dollars. But drag is not the only satellite problem. Energetic particles from the sun can damage solar panels, corrupt onboard electronics, and cause sudden charging events that can disrupt operations or, in extreme cases, permanently damage spacecraft. And then there are the human costs. During severe geomagnetic storms, airlines reroute flights away from polar regions. The radiation environment at high altitudes and high latitudes becomes unsafe for passengers and crew. Communication and navigation systems become unreliable. During the May 2024 storm, numerous transatlantic flights took more southerly routes, adding time and fuel costs. The May 2024 storm demonstrated this vulnerability in concrete terms. Farmers lost money. Satellites experienced degraded service. Radio communications blacked out. And that was a storm that, while severe, was nowhere near the magnitude of the Carrington Event. What would happen if a true Carrington-level storm struck today? The USGS has modeled this scenario using decades of geomagnetic data and Earth conductivity measurements. Their conclusion: the eastern and midwestern United States would be most vulnerable. The bedrock beneath these regions, particularly the corridor between Washington, D.C. and New York City, is more susceptible to the induced electric fields that damage transformers. This work demonstrates that an intense magnetic storm could be far more hazardous than what the electric power transmission industry is prepared for, said Jeffrey Love, a USGS geophysicist. These large storms are 100-year type events, so although rare, they are still potentially consequential. 100 years. The Carrington Event was 166 years ago. But here is the good news. Because there is good news, we are not helpless. Since the 1989 Quebec Blackout, significant progress has been made in protecting critical infrastructure. Power companies now monitor geomagnetically induced currents in real time. Protective protocols have been developed. Series compensation and blocking capacitors have been installed on vulnerable transmission lines. Hydro-Quebec itself invested hundreds of millions of dollars in grid hardening. Experts believe that if the 1989 storm happened today, the utility would not lose power. The modern grid is designed to withstand a 1-in-100-year geomagnetic event, and the March 1989 storm was estimated at roughly 1 in 40 or 1 in 50 years. Space weather forecasting has also improved dramatically. NOAA's Space Weather Prediction Center operates around the clock, monitoring the sun with an armada of spacecraft. The Solar and Heliospheric Observatory, launched in 1995, provides continuous views of the sun from a stable vantage point at the L1 Lagrange point, a million miles sunward of Earth. The GeoE satellites watch in X-ray wavelengths. The stereo mission provides three-dimensional views of coronal mass ejections. And then there is the Parker Solar Probe. This spacecraft, now deep within the sun's corona, is revealing the inner workings of our star in unprecedented detail. Its December 2024 closest approach, that Christmas Eve plunge to within 3.8 million miles of the solar surface, captured data that scientists are still analyzing. To appreciate what the Parker Solar Probe has accomplished, consider the engineering challenge. At its closest approach, the spacecraft experiences temperatures exceeding 2,500 degrees Fahrenheit. The heat shield, just 4.5 inches thick, made of a carbon-carbon composite sandwiching lightweight carbon foam, must protect instruments that operate at essentially room temperature. The thermal gradient across that thin barrier is extraordinary. At 430,000 miles per hour, the probe is traveling fast enough to fly from New York to Tokyo in under a minute. It is the fastest object humans have ever built. Every 3 months now, it will return to within 3.8 million miles of the Sun, gathering data during each close pass. And what has it found? Among the early discoveries were magnetic field structures called switchbacks, sudden reversals in the direction of the magnetic field that pervade the solar wind close to the Sun. These zigzagging field lines had been detected at greater distances, but their abundance and characteristics near the solar surface surprised researchers. The switchbacks appear to originate from features called magnetic funnels, concentrations of open magnetic field lines that channel material from the Sun's surface out into space. Understanding these structures is crucial because they may hold the key to one of solar physics' oldest mysteries: why the corona is so much hotter than the surface below it. The visible surface of the Sun, the photosphere, has a temperature of about 10,000 degrees Fahrenheit, but the corona, the diffuse outer atmosphere, reaches temperatures of 2 to 3 million degrees. This is counterintuitive. Normally, you expect temperatures to decrease as you move away from an energy source, not increase by a factor of several hundred. The answer appears to involve magnetic energy. The switchbacks and other magnetic phenomena observed by Parker Solar Probe suggest that energy is being released through continuous, small-scale magnetic reconnection events. Essentially, tiny solar flares happening constantly throughout the corona, heating the plasma to extreme temperatures. In December 2025, images from the probe revealed another surprise: material falling back toward the Sun after coronal mass ejections. When CMEs erupt, not all the magnetic material escapes. Some of it reconnects with the solar surface and rains back down, a process called inflow that had been theorized but never observed with such clarity. These breathtaking images are some of the closest ever taken to the Sun, and they're expanding what we know about our closest star, said Joe Westlake, director of NASA's Heliophysics Division. The data that will come down from the spacecraft will be fresh information about a place that we, as humanity, have never been. The mission is scheduled to continue through 2026 and potentially beyond, though eventually its thrusters will run out of fuel. When that happens, mission controllers plan to rotate the spacecraft so that its heat shield no longer provides protection. The instruments will be exposed to the full radiance of the Sun, and Parker Solar Probe will become a permanent fixture in the corona, an artificial object orbiting within the atmosphere of a star. But before that happens, it will have transformed our understanding of solar physics. It will have provided data that allows better prediction of solar storms. It will have answered questions that astronomers have been asking for centuries. We are learning rapidly how to read the Sun's moods. The typical warning time for a coronal mass ejection is 1 to 3 days. Enough time for power companies to reduce loads, for satellite operators to put spacecraft into safe modes, for airlines to reroute flights away from polar regions where radiation exposure is highest. The system works like this: coronagraphs, instruments that block out the Sun's bright disk to reveal the faint outer corona, detect CMEs as they leave the Sun. The large angle and spectrometric coronagraph on the SOHO spacecraft has been doing this since 1996. The stereo mission, with two spacecraft viewing the Sun from different angles, provides three-dimensional information about CME trajectories. Once a CME is detected, forecasters feed its observed speed, direction, and size into computer models. The WSA-ENLIL model, used operationally by NOAA, simulates the propagation of CMEs through interplanetary space. It can predict arrival times at Earth with useful accuracy, typically within plus or minus 6 to 12 hours. But there is a crucial limitation. The models cannot predict the magnetic field orientation of the incoming CME. And that orientation, specifically whether the field points northward or southward, is the primary determinant of how severe the resulting geomagnetic storm will be. This is where the Deep Space Climate Observatory comes in. DSCOVAR orbits at the L1 Lagrange point, about 1 million miles sunward of Earth. When a CME passes this location, instruments on DSCOVAR measure its magnetic field directly. This provides approximately 15 to 60 minutes of advance warning before the CME reaches Earth. Not much time, but enough for grid operators to take protective action. During the May 2024 storm, this system worked. Warnings were issued days in advance based on coronagraph observations. Satellite operators put sensitive equipment into safe modes. Power companies prepared to reduce loads if necessary. When the CME arrived and DSCOVAR confirmed a strong southward magnetic field, final protective measures were implemented. The May 2024 storm, despite its intensity, was the most successfully mitigated space weather storm in history, according to NOAA officials. Preparations worked, notifications were issued, protective actions were taken. This is the story that often gets lost in the drama of solar storms. We are getting better at dealing with them. Still, there are limits to what preparation can accomplish. The fundamental challenge is that we cannot predict exactly when the Sun will produce a Carrington-class event. We know these storms happen. Ice core evidence suggests major events occur on average every 500 years, with lesser storms more frequent. The Carrington Event was about 166 years ago. A similar or larger event, the Miyake Event of 774 AD, left chemical signatures in tree rings worldwide. We are, statistically speaking, due. And while we can harden infrastructure and improve forecasting, some vulnerabilities may be inherent to the technologies we have built. The long transmission lines that enable efficient electricity distribution are the same lines that pick up geomagnetically induced currents. The precise GPS signals that coordinate modern life are the same signals that can be scrambled by ionospheric disturbances. There is also the question of societal resilience. The 1989 Quebec blackout lasted 9 hours. It was inconvenient, disruptive, but ultimately manageable. But modern systems are far more interconnected and far less tolerant of extended outages. Just-in-time supply chains have minimal buffers. Digital systems require continuous power. Data centers back essential services that, in 1989, did not exist. Consider the cascading effects. Without electricity, water treatment plants cannot operate. Within days, municipal water supplies become unsafe. Without fuel pumps, which require electricity, vehicles cannot be refueled. Without refrigeration, food spoils. Without communications, coordination becomes impossible. Hospitals run on backup generators, but those generators need fuel, and fuel delivery requires vehicles, which need functioning fuel pumps. In 1859, the world could survive without telegraph. In 1989, Quebec could survive 9 hours without power. But in 2026, the vulnerabilities have multiplied exponentially. The July 2024 CrowdStrike software failure, in which a faulty update crashed Windows systems worldwide, offered a glimpse of how dependent we have become on continuous digital operation. Flights were cancelled, hospitals were disrupted, banks went offline. And that was a software bug, not an attack from 93 million miles away. What happens when the lights go out for weeks instead of hours? This is not fear-mongering, it is risk assessment. And risk assessment requires acknowledging both the probability and the consequences of unlikely events. A study conducted by Lloyd's of London examined the economic impacts in detail. Their modelling suggested that a Carrington-level event could leave 20 to 40 million Americans without power for periods ranging from 16 days to 1 to 2 years. The total economic cost was estimated at 0.6 to 2.6 trillion, roughly comparable to the 2008 financial crisis in magnitude, but concentrated in physical infrastructure damage rather than financial system failures. Let us return to the Sun. As we enter 2026, Solar Cycle 25 is transitioning from its maximum phase into a gradual decline. Sunspot numbers will decrease over the coming years. The frequency of major flares will diminish. By roughly 2030, we will reach solar minimum, the quiet phase of the cycle. But declining does not mean inactive. Some of history's most powerful solar storms have occurred during the declining phase of cycles. The magnetic field configurations that produce extreme events do not require peak sunspot numbers. A single complex active region, positioned correctly, can generate a Carrington-level storm regardless of where we are in the cycle. In fact, there are reasons to believe that the declining phase may be particularly hazardous in certain respects. As the cycle progresses from maximum toward minimum, the Sun's global magnetic field is reorganizing. The polar field reversal has occurred, but the new polar fields are still strengthening. Coronal holes, regions of open magnetic field that allow the solar wind to escape more easily, tend to become more prominent during this phase. These coronal holes can produce high-speed solar wind streams that, while less dramatic than CMEs, can still trigger moderate geomagnetic storms over extended periods. The November 2025 storms illustrated this point. Sunspot region AR4274 produced 4 X-class flares in just a few days, including an X5.1, the strongest flare of 2025. The resulting geomagnetic storms reached G4 levels with auroras visible from Mexico, and this occurred well past solar maximum. Scientists estimate that solar maximum actually occurred in October 2024. Everything since has been the beginning of the decline. Yet the Sun has continued to produce major events with regularity. Meanwhile, the Sun continues to reveal its secrets. NASA's Parker Solar Probe will complete 2 more close approaches at its record distance in 2025 before its mission enters an extended phase. The data flowing back is unprecedented. Scientists have observed magnetic field switchbacks, zigzagging field lines that provide clues to how the solar wind is heated and accelerated. They have witnessed coronal mass ejections from inside the Sun's atmosphere. They have measured conditions that, until now, could only be theorized. The European Space Agency's Solar Orbiter, launched in 2020, is providing complementary views from higher latitudes. Together, these missions are building a picture of our star that would have been unimaginable to Richard Carrington in 1859. We are, in a very real sense, learning to know the Sun for the first time, and perhaps that is the most important thing to understand. The Sun is not behaving strangely. It is behaving like a star. It has always done this. It will always do this for 5 billion more years until its hydrogen fuel is exhausted and it swells into a red giant that will engulf Mercury, Venus, and possibly Earth. What is changing is our awareness. For most of human history, the sun was simply there, a constant, reliable source of light and warmth. We did not know about its fusion core, its magnetic dynamo, its 11-year cycles of activity. We could not see its corona, could not detect its solar wind, could not imagine that electromagnetic radiation from 93 million miles away could set our telegraph stations on fire. Now we know. We know that we orbit a variable star. We know that this star occasionally throws tantrums. We know that these tantrums can, under the right circumstances, disrupt or damage the technological systems upon which modern civilization depends. And we know something else too. We are not unique. Every star in the night sky is a sun. Some are more violent than ours. Red dwarfs like Proxima Centauri are notorious for their intense flare activity, regularly producing outbursts that would strip the atmosphere from any planet in the habitable zone. Others are more sedate. Our sun is relatively well behaved as stars go. It is a G-type main sequence star in the prime of its life, with billions of years of stable hydrogen burning ahead. The 11-year cycle, while occasionally inconvenient, is relatively predictable. We have never recorded a super flare from our sun, an eruption thousands of times more powerful than anything we have measured. But we cannot rule it out. Studies of sun-like stars elsewhere in the galaxy have shown that some do produce super flares. Whether our sun is capable of such an eruption, and if so, how often, remains an open question. Tree ring and ice core evidence suggest that events far more powerful than Carrington occur on timescales of centuries to millennia. The Miyake events of 774 and 993 AD were perhaps 10 times more powerful than the Carrington event. If such an event struck today, our preparations would be insufficient. The consequences would be measured not in millions of dollars of transformer damage, but in months or years of recovery time. This is the ultimate context for understanding Solar Cycle 25. It is not about whether this particular cycle is slightly more or less active than predicted. It is about the fundamental reality of living in the atmosphere of a star. This knowledge is both humbling and empowering. It is humbling because it reminds us of our place in the cosmos. We are not separate from the universe. We are embedded in it. The same sun that grows our food and powers our solar panels can also, without malice or intent, shut down our power grids. The same magnetic field that creates beautiful auroras can also scramble our satellites. But the knowledge is also empowering because it allows us to prepare, to build more resilient systems, to monitor the sun's activity, to issue warnings, to take protective action. The question is not whether another major solar storm will occur. It will. The only question is when. So, should we be worried about what the sun is doing in 2026? The honest answer is, not particularly worried, but definitely attentive. The current solar activity, while exceeding predictions, is not historically unprecedented. We have faced similar levels before, and will face them again. The May 2024 storm, for all its drama, was managed successfully. Infrastructure held. Lives were not lost. The lights stayed on, mostly. But the fact that we weathered one storm does not mean we are prepared for all storms. The Carrington event was roughly twice as intense as anything we have experienced in the modern technological era. A Miyake-class event would be larger still, and while such events are rare, they are not impossibly rare. The Lloyds of London report estimated the return period for a Carrington-level storm at roughly 150 years, with a reasonable range of 100 to 250 years. That means there is a non-trivial probability, perhaps 1 to 2% per year, of such an event occurring during any given solar cycle. Those are not odds you can ignore. The prudent response is not panic, but preparation. Continued investment in space weather monitoring, hardening of critical infrastructure, development of protocols for emergency response, stockpiling of essential replacement components, particularly large transformers, and, perhaps most importantly, public awareness. The Federal Energy Regulatory Commission has taken steps in this direction. In 2016, after years of advocacy by scientists and engineers, EFERC ordered the North American Electric Reliability Corporation to develop standards requiring power grids to be protected from solar storms. Utilities are now required to assess their vulnerabilities and implement protective measures. Progress has been made, but challenges remain. The standards currently in place are designed for a 1-in-100-year event, roughly equivalent to the March 1989 storm, or somewhat larger. A true Carrington-level event, estimated at roughly 1 in 150 years, would exceed these design parameters, and a Miyake-class event, the kind that left its signature in tree rings in 774 AD, would be an order of magnitude beyond anything we have planned for. Some utilities have installed blocking devices that can prevent GICs from entering transformers. Others have developed operational procedures for reducing grid loading when solar storms are forecast. But implementation is uneven, and the interconnected nature of the grid means that vulnerabilities in one region can cascade into problems elsewhere. Meanwhile, scientists continue to push for better understanding and better prediction. The European Space Agency's Solar Orbiter mission, launched in 2020, is providing views of the Sun from high latitudes that complement the equatorial observations from other spacecraft. The combination of Solar Orbiter and Parker Solar Probe data is allowing researchers to build three-dimensional models of coronal mass ejections that may eventually improve arrival time predictions. Research into the Miyake events is revealing just how powerful solar storms can become. Analysis of tree rings and ice cores has identified at least a half-dozen events in the past 15,000 years that were significantly more powerful than the Carrington event. Understanding what causes these extreme events and whether they can be predicted is an active area of research, and on the ground, networks of magnetometers continuously monitor Earth's magnetic field, providing real-time data on the progress of geomagnetic storms. This data feeds into models that estimate GIC flows in power grids, allowing operators to take protective action when conditions deteriorate. Because the Sun is not going to stop being a star, it is not going to stop producing solar flares and coronal mass ejections. It is not going to stop occasionally reminding us that we are small and fragile and utterly dependent on forces we cannot control. What we can control is how we respond. On December 24th, 2024, as the Parker Solar Probe hurtled through the Sun's corona at speeds no human object had ever achieved, it carried with it a piece of human ambition and human curiosity. We had reached out to touch a star, and the star, in its own way, was reaching back. The data streaming home from that spacecraft will keep scientists busy for years, It will refine our models, correct our assumptions, reveal processes we had never imagined. It will make us, slowly and incrementally, better at predicting what our nearest star will do next, but it will not eliminate the fundamental uncertainty. The sun remains, in many ways, as mysterious as it was when Richard Carrington first saw those brilliant white flares erupt from its surface in 1859. We know so much more than he did, and yet there is still so much we do not know. Perhaps that is the final lesson. We live beside a nuclear furnace that has been burning for 4.6 billion years. It will continue burning for another 5 billion. On that timescale, our entire civilization is less than an eye blink. Our worries about solar cycles and geomagnetic storms are, cosmically speaking, vanishingly brief. And yet they matter. They matter because we are here, now, building a world that depends on systems the sun can disrupt. They matter because the risks are real, even if the probabilities are small. They matter because, unlike any species before us, we have the knowledge and the capability to prepare. The sun is not behaving strangely. It is behaving exactly as a star should. The question is whether we are behaving as wisely as a technological civilization must, with humility, with foresight, and with the recognition that the universe owes us nothing, not even a warning. There is something profound in this realization. For most of human history, we have been at the mercy of forces beyond our comprehension. Our ancestors attributed storms to angry gods, eclipses to cosmic omens, plague to divine punishment. The scientific revolution changed our relationship with nature, not by eliminating these forces, but by allowing us to understand them. We now know what the sun is. We know why it produces flares and coronal mass ejections. We know how these phenomena affect Earth. We can predict them to some degree. We can prepare for them to some degree. We can protect ourselves to some degree. But there are limits. The sun does not care about our satellites. It does not care about our power grids, our GPS networks, our carefully constructed technological civilization. It is a ball of plasma 93 million miles away, doing what stars do, following the laws of physics that govern all matter and energy in the universe. Our vulnerability is real, but so is our capability. We have built spacecraft that can fly through the corona of a star. We have developed warning systems that can predict solar storms days in advance. We have engineers working to harden our infrastructure against geomagnetically induced currents. We have scientists unlocking the mysteries of the solar dynamo. This is the human project, to understand the universe, to find our place within it, and to build a civilization robust enough to survive its occasional violent outbursts. The sun rises tomorrow, as it has for 4.5 billion years. Its light will take 8 minutes and 20 seconds to reach your face. And somewhere within that light, carried on waves of electromagnetic radiation, will be the echoes of processes so vast and so violent that they defy human comprehension. We cannot control the sun, but we can understand it. We can prepare for it. We can, in our limited human way, learn to live with the star that gives us life. That in the end is all any of us can do. And perhaps that is enough. Look up tonight, if you can. Find a dark place, away from city lights, and consider that every star you see is a sun, burning hydrogen, generating magnetic fields, producing flares and eruptions invisible across the vast distances of space. We are creatures of a universe that is indifferent to our existence, but we are also creatures capable of wonder, of understanding, of preparation. The sun will keep doing what it does. The question is what we will do. Choose wisely.